In the early hours before sunrise, while most of southern Naples remained quiet, instruments beneath the sprawling urban landscape registered a pair of subtle but unmistakable movements. At 4:32 in the morning, a tremor measuring magnitude 3.3 rippled through the subsurface. 6 minutes later, a second followed at magnitude 2.6. The numbers alone may appear modest, barely noticeable to many residents, yet their timing, location, and geological context raise questions that extend far beyond their immediate impact. Why do these tremors cluster in such short intervals? Why here, beneath one of Europe's most densely populated volcanic regions? And what do these signals reveal about the deeper processes unfolding beneath the surface? The area in question, Campi Flegrei, is not a conventional volcanic system defined by a single peak or crater. Instead, it is a vast caldera, an expansive sunken landscape formed by ancient eruptions, stretching across western Naples and extending beneath the sea. Within this terrain lies a network of craters, vents, and hydrothermal features, all part of a dynamic system that has been active for thousands of years. Unlike more visually imposing volcanoes, its activity is often expressed not through dramatic eruptions, but through subtler signals: gradual ground uplift, shifting gas emissions, and recurring clusters of small earthquakes. The two tremors recorded overnight are part of this broader pattern. While each individual event falls within a low magnitude range, their occurrence contributes to an ongoing sequence of seismic activity that has been increasing in both frequency and complexity over recent decades. Since the mid-2000s, the ground across portions of Campi Flegrei has risen by more than 1 meter, over 3 feet, measured through a combination of satellite observations and ground-based instruments. This vertical movement, known as bradyseism, has long characterized the region, with cycles of uplift and subsidence documented over more than 1,000 years. Historical records and geological data reveal that such cycles are not unusual. Periods of uplift occurred in the mid-20th century, including intervals between 1950 and 1952, 1969 and 1972, and again between 1982 and 1984. These episodes were marked by increased seismic activity, in some cases prompting precautionary evacuations as authorities responded to the uncertainty surrounding the evolving conditions. Each cycle eventually subsided without culminating in a major eruption, yet none followed exactly the same pattern. The current phase, which began around 2005, is distinguished not only by the scale of uplift, but by the rate at which seismic activity has intensified. Earthquake records indicate a non-linear trend. As the ground continues to rise, the frequency of earthquakes has increased at a faster pace than the uplift alone would suggest. This divergence challenges earlier assumptions that seismicity in the area could be directly predicted based on vertical ground movement alone. Beneath Campi Flegrei lies a complex magmatic and hydrothermal system extending from shallow crustal depths down into the upper mantle. Rather than a single, large magma chamber, the system consists of multiple reservoirs containing molten rock, gas, and superheated fluids. Current evidence suggests that the ongoing uplift is primarily driven not by fresh magma rising toward the surface, but by increasing pressure within a gas-rich zone located approximately 3 to 4 kilometers below ground level, roughly 1.8 to 2.5 miles in depth. This pressurization exerts stress on the surrounding rocks, gradually deforming the crust and creating conditions conducive to fault movement. As stress accumulates, fractures within the rock begin to slip, generating earthquakes. However, the relationship between stress buildup and seismic release is far from straightforward. Over the past century, observations have shown that the crust does not respond in a purely elastic or predictable manner. Instead, it exhibits behavior influenced by the physical properties of faults, including frictional resistance and the history of previous stress cycles. One concept that helps explain long-term patterns in the region is the Kaiser effect, a principle from rock mechanics, describing how materials remember the highest level of stress they have previously experienced. In the context of Campi Flegrei, this suggests that seismic activity tends to resume once stress levels exceed those reached during earlier uplift phases. While this framework provides insight into the general relationship between ground deformation and earthquake occurrence, it does not fully account for the accelerating rate of seismicity observed since the mid-2000s. To better understand this discrepancy, recent research has incorporated models that simulate the frictional behavior of faults under changing stress conditions. These models, often referred to as rate and state formulations, consider how the strength of a fault evolves over time, depending on factors such as slip velocity and contact properties between rock surfaces. When applied to the Campi Flegrei system, they indicate that even gradual increases in stress can lead to disproportionately large increases in seismic activity, particularly when faults approach critical thresholds of instability. Yet the overnight tremors and similar events are not solely the result of long-term stress accumulation. Many earthquakes in the region occur in clusters or swarms over relatively short periods. These swarms can involve dozens or even hundreds of small events, sometimes concentrated within hours or days. Unlike the broader trend of increasing seismicity linked to uplift, swarm activity does not always correlate directly with ground movement. Instead, it appears to be influenced by localized processes, including the movement of fluids through fractures and the interaction between individual earthquakes. When one earthquake occurs, it can alter the stress distribution in surrounding rocks, making nearby faults more or less likely to slip. This chain reaction can produce sequences of aftershocks, where each event triggers additional ones in a cascading pattern. Statistical models designed to capture this behavior treat earthquakes as part of an interconnected system, where the probability of future events depends on the timing and magnitude of previous ones. By combining long-term models of stress evolution with short-term models of earthquake interaction, researchers have been able to reproduce many of the patterns observed in Campi Flegrei over the past several decades. These hybrid approaches draw on extensive datasets, including earthquake catalogues dating back to the early 20th century and precise measurements of ground deformation collected through leveling surveys and global positioning systems. Together, these records provide a detailed picture of how the region has evolved over time, revealing both persistent trends and episodic fluctuations. The ability to simulate these patterns has practical implications for assessing seismic hazard. While it remains impossible to predict the exact timing or magnitude of individual earthquakes, probabilistic models can estimate the likelihood of different scenarios over defined periods, such as weeks or months. For a region like Campi Flegrei, where hundreds of thousands of people live within the caldera and surrounding areas, even incremental improvements in forecasting capability are significant. Despite these advances, uncertainty remains a defining feature of the system. The interplay between magmatic processes, fluid dynamics, and fault mechanics creates a level of complexity that resists simple interpretation. Each new tremor, including the pair recorded overnight, adds another data point to an evolving sequence that scientists continue to analyze in real time. The location of Campi Flegrei, beneath a major metropolitan area, amplifies the importance of understanding these signals. Naples, with a population of approximately 900,000 people, sits partially atop this restless caldera. Surrounding communities extend across its rim and flanks, forming a densely populated region where infrastructure, housing, and daily life intersect directly with geological processes occurring kilometers below. Monitoring systems in the area track a wide range of indicators, from seismic vibrations and ground deformation to gas emissions and temperature changes. These networks are designed to detect subtle shifts that may indicate changes in the state of the volcanic system. The two tremors recorded in the early morning hours fit within the range of activity that has become increasingly common, yet their occurrence in close succession underscores the need to examine not just individual events, but the patterns they form collectively. Over the past 2 decades, the upward movement of the ground has been accompanied by an acceleration in shallow earthquakes, most occurring at depths of less than 3 kilometers or roughly 2 miles. This shallow focus places the source of the activity relatively close to the surface, increasing the likelihood that even moderate events could be felt by residents. While the majority of these earthquakes remain low in magnitude, their cumulative effect contributes to a growing awareness of the system's ongoing evolution. Comparisons with past episodes provide context but not certainty. The uplift phases of the 20th century eventually stabilized without leading to a major eruption, yet the geological record also documents instances where prolonged deformation preceded volcanic activity. The most recent eruption in the area occurred in 1538, when the cone of Monte Nuovo formed following decades of ground uplift between 1400 and 1536. That event reshaped the local landscape, creating a new landform within a matter of days. Although the current situation shares some similarities with historical patterns, differences in scale, rate, and underlying processes complicate direct comparisons. The modern monitoring era provides far more detailed data than was available in the past, revealing nuances that were previously undetectable. This expanded perspective has led to the recognition that Campi Flegrei operates as a system with multiple interacting components rather than a single uniform mechanism. As the sequence of small earthquakes continues, attention remains focused on how these events fit into the broader trajectory of the caldera's activity. The two tremors that occurred within minutes of each other are part of a continuum that extends back years and even decades, each event contributing to a cumulative record of change. Whether they represent a routine fluctuation within an ongoing cycle or a subtle shift toward a different phase of behavior is a question that depends on patterns still unfolding. Data collected from seismic networks show that earthquake magnitudes in the region rarely exceed moderate levels, with most events remaining below magnitude 4. However, the potential for larger earthquakes cannot be excluded, particularly as stress continues to build within the system. Probabilistic assessments derived from combined modeling approaches suggest that the likelihood of stronger events increases as both uplift and seismicity accelerate, though precise thresholds remain difficult to define. At the same time, the role of fluids within the system remains an area of active investigation. The movement of gas and hydrothermal fluids through fractures can alter pressure conditions rapidly, triggering localized seismic swarms independent of long-term trends. These processes introduce an additional layer of variability, where short-term fluctuations can occur even in the absence of significant changes in overall uplift. The interaction between these different mechanisms, gradual pressurization, fault friction dynamics, and fluid migration, creates a system that is both dynamic and sensitive to small perturbations. In such an environment, even minor earthquakes can carry significance beyond their immediate magnitude, serving as indicators of how stress and pressure are being redistributed underground. As the sequence of small earthquakes continues to unfold beneath Campi Flegrei, attention increasingly shifts from isolated events to the patterns that emerge over time. The pair of tremors recorded within minutes of each other forms part of a broader clustering behavior that has become more pronounced in recent years. These clusters, often described as swarms, differ from traditional earthquake sequences in that they do not always begin with a single dominant shock followed by diminishing aftershocks. Instead, they can consist of numerous events of comparable magnitude distributed irregularly over hours or days, reflecting a more complex interplay of forces beneath the surface. Seismic records indicate that since the mid-2000s, the number of recorded earthquakes in the region has risen significantly, with annual totals increasing alongside the steady uplift of the ground. This trend is not linear. Periods of relative quiet are punctuated by bursts of activity, during which dozens of tremors may occur in rapid succession. The two overnight earthquakes align with this behavior, appearing not as anomalies, but as part of an evolving sequence in which timing and proximity carry as much significance as magnitude. The depth distribution of these earthquakes provides additional insight. Most events occur at shallow levels, generally within 3 kilometers, or approximately 2 miles of the surface. This concentration suggests that the processes driving seismicity are occurring within the upper portion of the crust, where pressure, temperature, and fluid movement interact in a confined space. Unlike deeper tectonic earthquakes, which are often associated with large-scale plate movements, these shallow events are closely tied to local conditions within the volcanic system. One of the defining characteristics of Campi Flegrei is the presence of a gas-rich reservoir beneath the surface. Located at depths of roughly 3 to 4 kilometers, about 1.8 to 2.5 miles, this reservoir contains a mixture of volcanic gases and fluids under pressure. As pressure inside this system increases, it exerts force on the surrounding rock, gradually deforming it and creating the conditions necessary for fractures to slip. Each slip releases energy in the form of an earthquake, contributing to the ongoing sequence of seismic activity. Measurements of ground deformation show that uplift is not uniform across the caldera. Certain areas experience more pronounced elevation than others, indicating that pressure is not distributed evenly. This uneven distribution can lead to localized stress concentrations, where faults are more likely to reactivate. When stress reaches a critical threshold, even a small perturbation, such as the migration of fluids or the occurrence of a nearby earthquake, can trigger additional events. The interaction between earthquakes themselves plays a crucial role in shaping these sequences. When one event occurs, it alters the stress field in its vicinity, effectively redistributing forces across adjacent faults. Some areas may become more stable, while others move closer to failure. This process can initiate a cascade, where one earthquake increases the likelihood of another, creating clusters that appear to propagate through the crust. The short interval between the two tremors recorded overnight reflects this type of interaction, where temporal proximity suggests a possible linkage rather than coincidence. Long-term datasets reveal that similar patterns have occurred repeatedly over the past decades. By examining earthquake catalogues extending back to the early 20th century, researchers have identified recurring cycles in which periods of heightened seismicity correspond with phases of rapid uplift. However, the current phase stands out because of its sustained acceleration. The number of earthquakes has increased at a rate that exceeds what would be expected based solely on the amount of vertical displacement, indicating that additional factors are influencing the system. Among these factors is the change in the mechanical properties of faults over time. As rocks undergo repeated cycles of stress and movement, their internal structure can evolve, affecting how they respond to future loading. Laboratory experiments on rock samples demonstrate that friction along fault surfaces is not constant, but varies depending on conditions such as pressure, temperature, and the presence of fluids. In Campi Flegrei, where hydrothermal processes introduce water and gases into fractures, these conditions can change rapidly, altering the stability of faults and influencing the timing of earthquakes. The result is a system that exhibits both memory and sensitivity. Memory in the sense that past stress levels influence current behavior, and sensitivity in that small changes can produce disproportionate effects. This combination helps explain why seismic activity can accelerate even when the rate of uplift remains relatively steady. It also complicates efforts to interpret individual events, as each tremor is both a product of preceding conditions and a factor influencing what follows. The proximity of this activity to densely populated areas adds a layer of urgency to its study. Naples and the surrounding communities lie directly above this evolving system, making even minor earthquakes a matter of public awareness. While most tremors remain too weak to cause structural damage, their frequency can lead to cumulative impacts, including stress on buildings and concern among residents. Infrastructure such as roads, utilities, and historical structures must also contend with the gradual deformation of the ground, which can alter alignments and introduce long-term maintenance challenges. Historical precedents provide a framework for understanding potential future scenarios, though they do not offer precise guidance. During the uplift phase of the early 1980s, seismic activity intensified to the point where precautionary evacuations were implemented in certain areas. That episode eventually subsided without leading to an eruption, but it demonstrated how quickly conditions can change when multiple factors converge. Earlier cycles in the mid-20th century followed similar trajectories, each with its own variations in timing and intensity. Further back in time, the eruption that formed Monte Nuovo in the 16th century illustrates the capacity of the system to transition from gradual deformation to volcanic activity. The decades preceding that event were marked by uplift comparable in some respects to what is observed today. However, the causes behind that transition remain only partially understood, highlighting the limitations of direct comparison between past and present. If you found this video informative, make sure to like, share, and subscribe for more in-depth updates on developing geological events. Tap that hype icon to help this reach a wider audience and keep more people informed about what is happening beneath the surface.